Okay, hi everybody. A wee bit of a change from the usual multiple choice papers. We're going to have a little look at the 2019 written paper. That's section 2 in the National 5 physics paper. It's a 2.5 hour paper in total, so it's a pretty long slog. So we're going to break the written paper down into 3 parts. The first part will be the dynamics and space questions. The whole lot is 110 marks. But in this video we're just going to have a look at the first 4 questions then, all on dynamics and space. And remember, any data you need will be on the data sheet, and all your relationships are on the relationship sheet. Also make sure you have a go at the questions first, and then once you've done that you can come and compare your answers with mine, and hopefully I've got them all correct. Anyway, here we go. A quadcopter is a drone with 4 rotating blades. Part A, in a race, the quadcopter is flown along a route from point A to point E, as shown in the diagram there, not to scale. So I'm going to put a start and a finish point on it. There is our start to finish vector. And let's see what we're asked then. We are asked, by scale diagram or otherwise, determine the magnitude of the resultant displacement of the quadcopter from point A to point E. So it's only the magnitude of the displacement we want first for 2 marks. That just means the size of the vector. So the size of that red line that I've drawn on the previous page there. Now it's a pretty complicated diagram, but we can make life easier for ourselves if we kind of chop it into a right angle triangle. So I'm going to add a dotted line there. Because in reality what this quadcopter has done is it has gone 11 metres down the way and then 6 metres back upwards. So that dotted line is actually 5 metres in length. And we could say the same thing horizontally. It's gone 16 metres from left to right and then 4 metres back the way. So the horizontal side of that right angle triangle is only 12 metres long. Now, if we just think about that right angled triangle then, we can either do a scale diagram or we can use a little bit of trigonometry. So, let's draw a little triangle first. Let's recreate that right angled triangle. So remember, it's 12 metres long and it's 5 metres down the way. And our 2 options here are, remember, scale diagram, or we can use Pythagoras to find the length of that line. So if we do a scale diagram and we have 1 centimetre representing 1 metre, then if you just measure the length of that resultant vector, it's 13 centimetres long, so the magnitude of the displacement is 13 metres. And if you want to do it using the Pythagoras method, then don't forget a squared equals b squared plus c squared, so 12 squared plus 5 squared is 169, and the square root of that to get the length of side A is 13 metres. So you'll get the same answer with both, just take care if you're drawing a scale diagram there. That's the magnitude of the displacement, 13 metres. And a part 2 of the question is by scale diagram or otherwise determine the direction of the resultant displacement. So let's use the same triangle. I'm going to put a little grid on at my starting point, and I'm going to use that grid as a kind of reference, because direction is measured from your start point, and it's that angle there we're interested in. Now if you've done a scale diagram, you can measure it directly with a protractor and you'll get 23 degrees, but you've got to have a protractor with you in order to do that, and you have to draw your diagram very carefully to scale. Your other method of doing it is by using SOHCAHTOA. Now because we know all 3 sides of that triangle now, we could use either sine, cos or tan, but I'm going to use the tan of the angle as the opposite over the adjacent. The opposite side is the 5, the adjacent is the 12. So 5 over 12, and then if you shift tan that on your calculator, then you find the angle A equals 23 degrees. Same as the scale diagram answer. So either of them would do. Now, should we just leave it as 23 degrees? There's a north on the diagram. And so really angles should be measured relative to north. Let me sketch a wee compass point here. And the compass points have all got numbers based on 360 degrees in a circle. So north is 0, east is 90, south is 180, west is 270. So if we want to express the direction of a vector, we should really express it from north, measured in a clockwise direction. So we've got 90 degrees from north to east, and then another 23. So our direction is 90 plus 23, that's 113. That's it expressed as a 3-figure bearing. Or you could also say it's 23 degrees south of east. That's a bit more clunky to say, and you need to know your compass points for that. So either of them would be acceptable, but directions are important. And make sure you state your direction relative to some point, usually north. Okay, pretty tough start. 1 part B, quadcopter takes 32.5 seconds to complete the race. Determine the average velocity of the quadcopter over the whole race. So if it's velocity, and this is a vectors question, we should really be saying velocity is displacement over time. Our displacement was the 13 from the previous part in the question, divided by the time, and if you do that on your calculator, you will get an answer of 0.4 meters per second. And because this is a vectors question, make sure you state the direction of the velocity vector as well. In vectors questions, don't forget about the direction. Part C. A second quadcopter completes the race at an average speed of 1.25 metres per second. The distance this one travels is 37 metres, and we've to determine the difference in the times taken between the two quadcopters. So let's do average speed equals distance over time for the second quadcopter. Its average speed was 1.25, it covered 37 metres. So let's rearrange that and work out the time. 37 over 1.25 is 29.6 seconds. And let's compare that with the first quadcopter. The first one took, let's have a look up, 32.5 seconds. And we're asked for the difference between the two. So we'll just subtract one from the other and we get 2.9 seconds. That's the difference between the two times. Okay, moving on. 1 part D. After passing point E, the quadcopter hovers at a constant height. I'm going to sketch one here showing the forces on it. So there will be a lift force on it, and there's the weight of the quadcopter acting downwards. And if it's at a constant height, the lift force and the weight are balanced. Or you could say that they are equal and opposite. That's a 1 mark question. Make sure if you want to say the forces are equal, you say equal and opposite. Question 2, still on dynamics and space. A glider is accelerated from rest by a cable attached to a winch, and the graph shows the horizontal velocity of the glider for the first 20 seconds of its motion. The glider is accelerated by a constant unbalanced force of 925 newtons, and we've to show that the initial acceleration of the glider is 2.5 meters per second squared. So we're going to be using the slope part of the graph to work out the acceleration. So let's make a little list of all the information that we need. We know the initial speed is 0 and the final speed is 24 meters per second. That's the maximum speed it reaches, and we're looking for the acceleration and the time it took to reach that final speed of 24 is, that's quite difficult to read, I think that's about 9.5 seconds, 9.5 seconds. And then we're going to use our acceleration relationship from the relationship sheet and substitute in our values. 24 minus 0 over 9.5, that gives us our acceleration of 2.5 meters per second squared. Now watch out here, because your calculator will tell you an answer. It's a big long answer with loads of numbers after the decimal point. Under no circumstances write that down. Write down the answer that you're asked for. 2.5 metres per second squared. Okay, then we have to calculate the mass of the glider. We've just worked out the acceleration, and we know the unbalanced force. We were told there's a constant unbalanced force of 925 newtons. There's the acceleration, so we can use F equals ma. Substitute in first if you want to guarantee yourself that second mark. 925 equals the mass times the acceleration of 2.5 metres per second squared, and then rearrange it. So m equals F over 8, 925 over 2.5. And if you do that in the calculator, you'll get an answer of 370 kilograms. That's the mass of the glider. Question 2a. At 2 seconds, the cable pulls the glider with a force of 1,200 newtons, and we've to determine the size of the frictional force acting on the glider at this time. Now, all the bits of this question are linked. This is part 3, so we need information from previous parts, maybe part 2 or part 1, in order to do this. So, if we've to work out the frictional force, remember the unbalanced force was 925 newtons. So if 925 is the unbalanced force, then that's the difference between the forward force and the frictional force. So let's do 1200 take away 925. That means our friction must be 275 newtons. And then suggest one design feature of the glider that reduces any friction on it. Well, an aerodynamic smooth shape or a streamlined body would do. Part B. At 8 seconds the glider reaches its takeoff speed and leaves the ground. Determine the distance the glider travels along the ground before takeoff. Well, we were given a graph right at the beginning of the question, and you can work out the distance gone by an object from its velocity time graph by working out the area under the graph up to the time we're interested in, which is 8 seconds in this case. So that's while it's still accelerating. So distance gone is the area under the speed time graph or velocity time graph, and it's 8 seconds we're interested in. So if we look along at 8 seconds, well, let's zoom in on this graph a wee bit and let's put the 8 seconds on. That's there. And then the velocity at that time is 20 metres per second. So let's use that information and work out the area under the graph up to that point. So it's that area there we're interested in. Remember, the area of a triangle is a half the base times the height. In this case, that's a half times 8 times 20, which is 80, and therefore the distance gone is 80 metres. So, and we should really answer the question where we're asked to write the answer. Although I did it on the graph there, I should really replicate that down here. So there's the area under the graph. That's our 80 metres. Now, you could, of course, have done this using distance equals average speed times time. And because the final speed was 20 and it started from rest, then at 8 seconds, its final velocity was 20 metres per second. So its average speed or average velocity is only 10 metres per second. That's the average of its final and its starting speed. So if we do distance equals average speed times time, we get the same answer, 80 metres. So either answer would be accepted. Well, let's move on. Question 3. In 1971, the astronaut Alan Shepard hit a golf ball on the surface of the moon. Using your knowledge of physics, comment on the similarities and or differences between this event and hitting an identical ball on the surface of the Earth. Well, as soon as you see those 5 words, using your knowledge of physics, you know that this is an open-ended question, and it's really up to you what you put down, as long as it's relevant and at a suitable level, and it contains the physics that demonstrates your knowledge, then you can get yourself up to 3 marks here. So what sort of things could you be writing about? Well, if Alan Shepard's doing this on the moon, then gravity on the moon is less than the gravity on the Earth. On the moon, you could look it up on your data sheet, and gravity on the moon is only 1.6 newtons per kilogram. And so if the gravity is less, then for the same force the ball would go higher and further, as acceleration due to gravity is less on the moon. And the ball would be in the air for a longer period of time. Remember to write as much as you can in open-ended questions. Also, there's no air resistance on the moon, so there'll be no drag force slowing the ball down either on its upwards or its horizontal motion. It would be more difficult for the astronaut to hit the ball due to the constraints of a spacesuit. And you could also talk about the fact that the mass of the ball would be the same on the moon as it was on the Earth, but the weight of the ball would be less on the moon. And you could do a calculation to support that as well, I suppose. Try and include as much information as you can in open-ended questions. You could sketch the projectile path for both of them, and always go back to open-ended questions at the end of the paper if you've got time. Okay, question 4, this is the last one for this video. Astronomers are studying a distant star and analyse the light from the star that reaches the Earth, and the line spectrum from the star is shown along with the line spectra of the elements hydrogen, helium, mercury, calcium and sodium. And we have to determine which of these elements are present in the star. So the tip here is to very quickly identify which of the elements patterns does not fit into the star's line spectrum. So with calcium, there's an obvious set of lines there that isn't in the star, and with sodium there's a double line there that obviously isn't in the star. And then we'll have a look at the other 3 and then try and match up and see that line is present, so is that one, so is that one, and so is that one. So hydrogen is definitely in the star. And then do the same with the helium. Use a ruler would help you here as well to line up these individual lines in the spectrum. So there's helium in the star as well. And with mercury, then all the lines in Mercury's spectrum are also present in the star's line spectrum. So hydrogen, helium and mercury are all present in the star. So that's for part A, hydrogen, helium and mercury. Let's move on, part B. Well, the star is 97 light years from the Earth. State what's meant by the term light year. Well, a light year is a unit of distance, and it's the distance that light travels in 1 year. And then if we want to calculate that distance in meters from the star to the Earth, we can use the relationship distance equals speed times time. And because it's a light year, we use the speed of light, and we use the number of seconds that are in 1 year. That's how we would calculate 1 light year. So the number of seconds in a year is 60. 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365 days in a year. And if we want 97 light years, then we would multiply all of that by 97. And we're going to get an answer for the distance in meters. That's a huge number, and the reason it's a huge number is because the number of seconds in a year is a big number, and the speed of light is a big number. So when you do all that on your calculator, you get an answer of 9.18 times 10 to the 17 meters. Make sure you double check that on your calculator. Watch your significant figures as well. I think the speed of light on your data sheet is to 3 sig figs. The 97 is 2 sig figs, so don't go to too many significant figures there. Part C, astronomers use satellite-based telescopes to collect information about objects in space. Suggest an advantage of using satellite-based telescopes such as the Hubble Space Telescope, well, there's no atmospheric interference, there's no light pollution, no cloud cover, etc. And another use of satellites, well, there's loads you could put there. You could put satellite navigation systems, a GPS that's on your phone or in a car. There's global communication for live sporting events. Any suitable answer there would get you the mark. Question 5 is on electricity. We shall return to that in the next video. Hopefully you did okay. See you in the next one.